In the last video, we introduced the concept of a Cauchy sequence. Let's recall the definition. A sequence of points P1, P2, P3, etc. in a metric space E is called a Cauchy sequence if, given epsilon greater than 0, there is some positive integer n such that for all little m and n greater than capital N, the distance between P sub m and P sub n is less than epsilon. For practice, let's state what it means to not be Cauchy. So a sequence is not Cauchy if. So this is a good way to practice negating something. So take a moment and write down what you think it means for the sequence to not be Cauchy. Okay, let's go over the answer. So it's not Cauchy if there exists some positive integer epsilon such that for all positive integers n, for every positive integer n, there exist little m and little n greater than capital N such that the distance between P sub n and P sub m is greater than or equal to epsilon. So that's the definition to not be Cauchy. That's what you need to show if you want to show that a sequence is not Cauchy. Let's now talk about the connection between convergence and Cauchy. So the first proposition is that convergence implies Cauchy. So every convergent sequence is Cauchy. Every convergent sequence of points in a metric space is Cauchy. So that gives you lots of examples of Cauchy sequences. Just take any convergent sequence. All right, let's prove this. So the idea is, well, first we should introduce the sequence as opposed to P1, P2, P3, ... converges to P. Okay, we want to show it's Cauchy, so we let epsilon be greater than 0. Well, we know that, so we know that this sequence converges. So let's draw a little picture to get an idea of what to do. So here's, say, the limit P, okay? We want to show that eventually all the points are within, the points in the sequence are within epsilon of each other. Well, the idea is we know that all the points are eventually within epsilon of P. So actually, let's be a bit fancy and take epsilon over 2. So we look epsilon over 2 to the left. Okay, in this picture I'm working with real numbers, but this applies to any metric space. So we look epsilon over 2 units of P. And the idea is eventually we know that all the points in your sequence lie in this epsilon ball, or this epsilon over 2 ball centered at P. So, well, if you have a P sub n here and P sub m here, then how far away at worst are they from each other? Epsilon, right? So the idea is to use the triangle inequality because P sub n is within epsilon over 2 of P, P sub m is within epsilon over 2 of P. So the sum, right, P sub n, the distance between P sub n and P sub m must be at most epsilon away from each other. So that's the idea of the proof. So we know that there exists, so since the sequence converges, there exists capital N such that for all little n greater than capital N, the distance between P and P sub n is less than epsilon over 2. Okay, now we claim that this capital N works in the Cauchy criterion. So let little m and little n be greater than capital N, then the distance between p sub m and p sub n, well, we're trying to show it's less than epsilon. By the triangle inequality, this is less than or equal to the distance between p sub m and p plus the distance between p and p sub n. And then this is less than epsilon over 2 plus epsilon over 2, which is epsilon. So that completes the proof. So a pretty simple standard argument that's worth remembering. And again, it's worth remembering the idea. The idea is that eventually your points are within epsilon over 2 away from p. So then by the triangle inequality, the points are within epsilon away from each other. That's, in one sentence, the idea of the proof. So convergence implies Cauchy, but Cauchy does not imply convergent. Because, well, we've seen in the previous video what can happen. If you suppose you start off with a convergent sequence, right? And then you remove the limit. And you assume that none of the points are equal to the limit. Then you get a Cauchy sequence because that sequence was convergent, but it's not convergent in that new metric space. So for example, Cauchy does not imply convergent. One example would be to take R2, but then to only look at the upper half plane. Suppose you look at the upper half plane. Let's say this is E. It's the set of points x, y in R2 such that y is greater than 0. So you don't include this x-axis. Then you could just take like a sequence of points like this, or just down the y-axis that converges to 0, 0, but 0, 0 is not an E. So for instance, you can take a sub n to be all points of the form. You take a sub n to be the point 0, 1 over n. Then the sequence is Cauchy, but not convergent. Well, we've seen by the argument in the previous video that the sequence is not convergent because we know that the sequence converges to 0, 0 in R2, but 0, 0 is not in E. Okay. How do we know that this is Cauchy? Well, to prove that it's Cauchy, we basically apply, one thing you can do is you can just apply the argument in the statement, in the proof that convergence implies Cauchy using the point P as the limit. So in this case, the limit is 0, 0. So you could say, to show that the sequence AN is Cauchy, you could say let epsilon be greater than 0. Okay. So the distance between a sub n and a sub m is the absolute value of 1 over n minus 1 over m. And the idea is to make each of those less than epsilon over 2. So the idea is to let n, capital N, be greater than 2 over epsilon. And let little m and little n be greater than capital N. Then the distance between a sub m and a sub n is just going to be the absolute value of 1 over m minus 1 over n. And then by the triangle inequality, this is less than or equal to, well, 1 over m and 1 over n are positive, so we don't need the absolute value. 1 over m plus 1 over n, right? But each of these are, let's see, if m is greater than n, then 1 over m is less than or equal to 1 over, it's less than 1 over capital N. So it's less than 1 over capital N plus 1 over capital N, and 1 over capital N is less than epsilon over 2. So this is less than epsilon over 2 plus less than epsilon over 2. So the sum is epsilon. So that proves that the sequence is Cauchy. Okay. And again, going back to what I was saying before, you're essentially using the triangle inequality. In this case, your P is just 0, 0. So that's the idea here, right? The distance between P sub m and P, distance between P and P sub n. So I'm using these. But when you have P is just 0, 0, then these distances are just 1 over m and 1 over n. So that's a useful thing to keep in mind to prove that something is Cauchy. Okay, so convergence implies Cauchy, but Cauchy does not imply convergence. And it's a good idea to remember the proof of this proposition.